Okay, ELE 115. I want to talk about the RL series circuits. Try to help people out. This stuff is a little challenging if you've never seen it before. And so I'm going to take a look at Lab 5 and solve those circuits using the whiteboard setup we have there, which, by the way, I have placed in Blackboard. If you go into Blackboard, you will see that there is a Lab 5 AC RL series circuits. I don't know why the AC has got a slash there. It looks like air conditioning RL series circuits. But trust me, it's alternating current. So Lab 5 AC series RL circuit whiteboard analysis. This is what we're going to look at. And then I'm going to show you a simulation of that same circuit. And I'm just going to one more time walk through these calculations so you can see what's going on here. So anyway, this is going to be again about Lab 5 and RL series circuits, and I will record another lecture for RL parallel circuits, probably using the lab material for Lab 6, so that you can also understand what's going on there before you actually do the lab. Okay, so I'm going to put this down here. Oh, sorry. I'm not sure that I wanted to do that. So what I want to do is I want to look at that, first of all, the schematic for the lab, because I didn't write it on the whiteboard. But here's the schematic for the lab. We have a sinusoidal source, and it is driving out through a 1 k ohm resistor through a 10 millihenry inductor. It's at 20 kilohertz, and it's 10 volts peak to peak. Now this, actually, the way I simulated this might be 20, but now that'll show up in the simulation. But it really does, it's not so important what that voltage is as long as we use the same one all throughout the discussion. I'm going to use 10 volts peak to peak like the lab in the discussion. So this, let's get our whiteboard out there. And let me see if I can zoom in on this thing. I can. So I'm going to make this bigger and slide it over here. So we have a series circuit. Resistors are, as we've always said, things that turn electrical energy into heat energy immediately. And so there's no phase shift or delay going through resistors. Remember also that sine waves are great for this kind of analysis, because the sine wave is the one waveform, or sinusoids, that is, are the one waveform that when you put them into circuits containing resistors, inductors, and capacitors, which we'll learn about, the waveform that goes through the circuit at any point is always a sine wave or sinusoid. It's really neat property. And let's see here. I didn't want to shrink that down so much. I know what we'll do. We'll just do this. There we go. So now we have that. There's our circuit. So in a series circuit, if this were a resistor and this were a resistor, we'd add them together. But in steady state sinusoidal AC, and that's what we have here. We have a circuit that a sine wave has been driving this circuit for a long time, so there's no transient responses or anything. We have a steady state response. The problem we have is that things that have reactance, like inductors and capacitors, they have a 90-degree relationship to resistors. So we put our resistor on here at 1k ohm. We put 1k ohm on the x-axis, if you will, or what technically is the real axis, but that's okay. So I start and put my resistance here on the x-axis. I go back and look at my inductor, and I know that I need to get the AC resistance of this inductor, if you will, or its inductive reactance. And we'll make a graph, and I'll show you that in this graph, if we had capacitive reactance, we would compute it with a formula, and it would point down here at minus 90 degrees, and inductors, we compute their reactance and we put it at plus 90 degrees. And then we take a vector sum of these two quantities. Okay. If you've ever had any physics with some force problems in it, if I pull on a rope this way and you pull on a rope that way, the sum total force is in this direction, and so it's very similar with these voltages. So what we do here is first we calculate this inductive reactance, which is 2 pi times the frequency times the inductance. Well, for us, the frequency is 20 kilohertz, 20 times 10 to the third hertz. And the inductance is 10 times 10 to the minus 3, or 10 millihenries, thousandths of a henry. And 6.28 is a crappy approximation of 2 pi. So we multiply this all together, and the 10 to the positive 3 and the 10 to the negative 3 cancel each other out, because when you multiply powers of the same number, you add their exponents. When you divide powers of the same number, you subtract their exponents. So the answer that we get here is essentially 20 times 10, that's 200, times 6.28. Well, 200 times 6 would be 1200, so the end result is we get 1256 ohms, or 1.256 k ohms, however we're going to do it. But it's at 90 degrees, so we plot that up here. And it's kind of hard to see it, but I tried to make 4 marks this way to be, like 1,000 ohms is 4 times 250, and up here I tried to make 5 such marks to come out to 1250. This really should be 1256, obviously, but I'm just trying to do something that I can draw. And so I have this vector here, technically 1256 at plus 90 degrees, and the angle, this 90 degrees business, is measured counterclockwise, rotating from the x, or real axis, if you will. All right, so 90 degrees would be straight up. And now we go to figure this out. What I have here is a right triangle. Axes always meet at right angles for us anyway. And I have a right triangle. One side is 1,000, the other side is 1,256. And to find the hypotenuse, we use the Pythagorean theorem, where we know that z squared equals r squared plus xl squared, or the hypotenuse squared equals the square of one side plus the square of the other side. And I take the square root of both sides, and I get the hypotenuse. So we calculate that out, and we got 1,606 ohms, something in that area. And it's so we'll remember that. And we also need to know what angle we're at, because vector quantities, and that's what we're dealing with, are vector quantities. Vectors have magnitude and direction, and we just found the magnitude, 1,606 ohms, but we don't know the direction yet. So one of the ways of finding this angle is to find the angle whose tangent is this opposite 1256 divided by 1000. All right, because tangent equals opposite over adjacent. If you've ever heard the SOHCAHTOA mnemonic, TOA means tangent equals opposite over adjacent. So we want the angle whose opposite over adjacent is XL over R, the inductive reactance divided by the resistance. So we do that, and we says, what angle has a tangent of 1.256, and it turns out it's 51 and a half degrees. So our impedance, and impedance is, you have all these names, reactance and resistance. Reactance, of course, is kind of like the AC resistance of an inductor or a capacitor once you compute it. Impedance is a fancy name for a situation when you have both reactance and resistance. So I put down here combined resistance and reactance. We call it impedance, and it usually has the letter Z. So inductive circuit, the current lags the voltage. That's something to memorize because it gives you all four cases for inductive circuits and capacitive circuits. But this is one that I always remember. Current lags in an inductive circuit. So we now have our, this is kind of like our total resistance in the circuit, this total impedance. So we come over here and we say, well, let's do a little calculating, okay? And there's two ways to express vectors. You can give magnitude and direction, or you can break the vector down into, x and y coordinates, or x, y, and z coordinates if you're in 3 dimensions. When you break it down, I shouldn't say coordinates, when you break it down into components, that is called rectangular form. And in rectangular form, we would say this thing is 1,000 ohms on the real axis and 1,256 ohms on this imaginary axis or reactance axis. We have the two components. The other way to express that is to say that it's 1,606 ohms magnitude at an angle of 51.5 degrees. Okay, so let's go over here and look at this thing. When you're doing multiplication and division, polar form is best. When you're doing addition and subtraction, rectangular form is best. So let's go through what we have here. I think we're mostly doing division and that sort of thing, and that's going to be polar form. So I take my source, which is 10 volts peak to peak, and we always put our source at 0 degrees. I mean, why complicate things? So our source is 10 volts peak to peak at 0 degrees. Our total impedance is 1.6 k ohms, or 1,600 ohms, at 51.5 degrees. And so let's find, using Ohm's law, I equals V over R. Well, in AC circuits, I equals V over Z, because this total impedance is kind of like your total AC resistance. So I've got 10 volts peak to peak at 0 degrees for VT, my source voltage, and I've got 1.6 k ohms at 51.6 degrees. And when I do the calculation, I get 6.25 milliamps peak to peak. Now we got to keep peak to peak going through here. All right, be careful to do that. 6.2 milliamps peak to peak at an angle of 0 minus 51.5 degrees. Obviously, that's 6.25 milliamps peak to peak at negative 51.6 5 degrees. And that's where this comment down here, current lags voltage in an inductive circuit. And if you look at the voltage applied to the circuit is 0 degrees, but the current is behind it. It's at minus 51.5 degrees. You can think of things as rotating around counterclockwise here. So when the voltage is here at 0 degrees, the current is still down here at minus 51.5 degrees, and so on. And you'll see that in the scope trace. You'll see this this lag in the current. So just an important point for series series circuits. I total equals IR. So just you'll see that in the calculations here. The voltage across the resistor is equal to, technically you'd say in Ohm's law, well, it's equal to current through the resistor times the resistance, V equals IR. Turns out in a series circuit, the current through the resistance is also the total current. So VR is equal to IT times R, and we've got 6.25 milliamps peak to peak at minus 150 degrees times 1,000 ohms at 0 degrees. Resistors are at 0 degrees because there's just no phase shift in them. Okay, everything happens immediately. And when we multiply that out, we get 6.25 volts peak to peak at minus 51 degrees. Now, so the voltage across the resistor, this is an important point. Notice the voltage across resistor has the same phase as the current. And it should in a resistor. There's no phase delay, there's no delay and no shifting of the sine wave in a resistor. So VR and IR have the same phase, and that is why, by the way, VR, where's my, sorry, let me leave that there. VR and IR have the same phase. So that, and IR is the same thing as I total. So in a series circuit, whenever there's a resistance present, you can use the voltage across the resistor to get the phase angle of the current, because the resistor has no phase delay in it. That means the voltage across the resistor, VR over here, okay, is the same phase as the current through the resistor, and that's useful in the lab. Now let's so we got VIR. It's 6.25 volts peak to peak at minus 51.5 degrees, the same angle as the total current through the circuit. Now VL is equal to IT times XL, just like VR was IT times R. So we take 6.25 milliamps peak to peak at minus 51.5 degrees, and we multiply it by 1.256 k ohms at 90 degrees. Remember in our diagram, XL was standing up here at 90 degrees, okay? So, when I multiply those together, I get some number here, 7.85 volts peak to peak, and, minus 51.5 times 90, you add the two things together, and so you get positive 38.5 degrees, and that's to say the voltage lags in an inductor. I'm sorry, the current lags in an inductor, but the voltage leads. Okay, so furthermore, in the inductor, if you look at it, the current came through at minus 51.5 degrees, but the voltage is at plus 38.5 degrees, and due to that addition operation between the minus 51.5 and the plus 90, I got this thing here. The plus 90, it just goes to show you that the current and voltage in a reactor, that is in an inductive reactance or in a capacitive reactance, the current and voltage are 90 degrees out of phase. And we'll talk about that more. There's a little test one can do to see if they've got this stuff right. You can take VR squared plus VL squared, and you should, just have the original voltage there, okay? So, let's look at our simulation. I just want to see if there's anything else here. This was our setup, by the way. We had our sine wave generator. There was a node A in the circuit, and it went to scope channel number 1. There was a node B in the circuit, it went to scope channel number 2. And then there was a math function, which was channel 1 minus channel 2. And that's how we could pick up the voltage across the resistor and infer the current through the resistor, and therefore the total current of the circuit. So, let's take a look at our simulation here. Now, you might recognize this is, this is kind of what your scope looked like once everything was right. It's mustard here. I tried to make it yellow like our scopes, but it's as close as I get. So here's channel 1. It's driving everything. And I'm measuring from the peak of channel 1 to the peak of channel 2 right here. And channel 1, of course, is 0 degrees. Channel 2 is here. And so I'm at the peak of channel 1 and the peak of channel 2. I have these two cursors on here, and it tells me that the difference, cursor 2 minus cursor 1, is minus 5.25 microseconds. Now, the calculation I'm going to do here, I'm trying to think of how I can do this, but here's the idea. One period of our sine wave is 50 microseconds. It's at 20 kilohertz. You can work that out. 1 over 20 kilohertz. The period equals 1 over the frequency, and the frequency equals 1 over the period. Well, 1 over 20,000 is 50 millionths. Now we have a difference here of 5 1/4, about 5.25 microseconds. And I'm going to do a calculation where I'm going to say, what fraction is 5.25 out of 50? And so I'm going to do something like 5.25 divided by 50 equals, and it's about 0.105. Now, what portion is that of 360 degrees? Because one whole cycle, or 50 microseconds of that waveform, is 360 degrees. So I'm going to take that thing and multiply it by 360 degrees, and I get 37.8 degrees. I think if you remember in lab we got about 38. Well, here we can look at our calculation, right? What were we looking at here? So for VR2, for the voltage across the inductor, channel 2, we had, this is VL, we had plus 38.5 degrees. We calculated, and this is not a highly accurate measurement with this cursors on this picture thing. We got 37.8 degrees, so we're pretty close there. Now, let's see. So we're saying that this voltage across the inductor is leading us by 38 something, about 38 degrees. Now let's look at our next case. Okay. Now we're going to look at, if you remember, we used the math channel on the scope to get channel 1 minus channel 2, and I typed that incorrectly here. So let me fix it. I don't think I can fix it right now. I can fix that. Sure I can. Let me do a little band-aiding here. And then save that. Okay, so just like on your scope, the red was channel 1 minus channel 2, and I've used the cursors again to figure out where this phase would be. Here's the source voltage at 0 degrees, and then I go over here until to the peak of the channel 1 minus channel 2, which is essentially the voltage across R1. Here's channel 1, there's channel 2. The difference is, the voltage difference is the voltage across R1. So we measure the delay from the peak of the source to the peak of the voltage across channel 1 minus channel 2, the math channel, and we get really pretty close to 7.2 microseconds there. So let's just call it that. And once again, I'm going to find 7.2 microseconds divided by 50 microseconds gives me about 0.144. All right, it's it's not far from 1/7 of 360 degrees. So now I got to multiply that fraction that I just calculated of a cycle. I got 7.2 microseconds out of 50 microseconds, and I now have that fraction of a channel. So now I multiply that times 360, not fraction of a channel, fraction of a cycle. So I multiply that by 360 degrees, and I get 51.84 degrees. Now, if we go back to our whiteboard complete, we had our answer was 51.84, and the answer here was 51.5. So not too shabby, really. Okay, so that's and there's a little check one can do. You could say, if I calculated these things correctly, and you could take 6.25 squared plus 7.85 squared, is that equal to 10 squared, the source voltage? And we'll do it right now. I will take the square root of 6.25 squared plus 7.85 squared. So I'm taking the square root of the sum of that, and I come up with 10.034 volts. So that's pretty darn close to 10 volts. And that's a good check right there on what's going on. And furthermore, you can see that the voltage, because of this multiplication and computation there, these two guys add up to 90 degrees. If you look at it, they become 80. These two become 90 degrees. because across the inductor, the voltage across the inductor is, if the inductor were the purest thing, you know, like that it could be, then there would be a 90-degree phase shift between the voltage and the current in the inductor, and the current would lag and the voltage would lead, and that's, you know, that's what we have here. So this whole idea of the current and voltage being 90 degrees out of phase in an inductor or capacitor, you know, perfect inductor or capacitor, goes to this idea of power factor and that type of thing. If you have no resistance in the wire of your coil, then it's going to behave like an ideal coil, and you always have 90 degrees phase shift. But it's very typical for coils to have some resistance because they're made of wire. And, you know, not all inductors are coils. There are, you know, there are other types, but an inductor is usually made of wire, and that wire has resistance. Therefore, the inductor is not a pure inductor. A little bit of resistance is experienced. But don't worry about that. So that was the first part of the Lab 05, and I think we'll end here, and I'm going to make another video walking through one of the practice test questions, as I've posted. Let me go back to Blackboard. Whoops, that's a screenshot. That's not going to take me there. Okay. That also is a screenshot. So if I can find Blackboard in here somewhere, did I lose a... Here it is. So you saw this. This is where you can find that, you know, screenshot, you know, image from the 625 whiteboard that we just talked about. If we go up here to lab content, no, I know where we want to go. So sorry. We want to go to the lecture part of the course. This is it right here. So if we go to course content and go down to week 6, you'll find this section right here, resistive inductive practice circuit problems solutions. Somebody had emailed me and said they had some problems with these circuits, that they thought their calculations were right and some of the answers were a little iffy, and I think that may be true. So what I did is I just wanted to walk through here, because when I took this thing I got like 85 out of 100 for the two problems there. So this thing is I believe is a PDF. All right, that's what it is. And in our next video I will go through this. Thank you very much, and we'll call it quits there, and we'll see you in the next video.